most systems of equations and things of that sort that we have in nature tend not to be linear by their nature. You know, they come from, a lot of them come from differential equations, and you get either rather complicated or even, you know, rather simple equations, but not very many of them are linear. But when you're looking at the small scale of things, like if you're making a weather simulation or if you're doing something like setting up a Google search or something like that, you often convert these rather complicated formulas into linear equations. And so making linear approximations is really important from the standpoint that if you have to do 100,000 calculations within a very short period of time, you can do it because computers can do linear algebra very, very fast. And so if you're going to ever you know, do something like in biology or so where you're doing a large-scale growth model or things of that sort, you'll probably end up doing some linearizations there. So what we're going to do is we're going to take a single function with a single point and talk about how you linearize it, and then we'll leave the large-scale stuff up to later classes, depending on if you go into biology or economics or anything like that. So let's say we have this function here, and that's my blue line. Oops. Okay, so now what I'm going to do is I'm going to put this, I'm going to designate a point for a tangent. And then I'm going to put a line next to that tangent. Now, you know how to do this. You know how to figure out what's the slope of the line. You know how to figure out the equation of the line already. But let's look at it with slightly different terms. So I'm going to call that tangent line function capital L of x, all right? And that just means the linearization. It's a linear function. So here I'm assuming that, you know, my y-axis is plotting in blue the function and also the linearization in red. So with a tangent line, what we did was we used the point-slope form, and so we started with that equation, which you've seen a few times and have used a few times. And we say, okay, the slope is going to be the derivative evaluated at a. y1 is going to be the value of the function at a. And x1 is just going to be a, which is my value that I'm starting from. So if I just make the substitution with my point-slope form equation at the top, I just get this. There's nothing tricky about this. It's just substituting m, y1, and x1 and putting in either the function, the derivative, or the value of a itself. Now I'm going to do a rearrangement of this, and I'm just going to make this y equals f at a plus f prime at a times x minus a. So what this gives me then is that if I have my point a, my function and the derivative, I can take a value x and I can calculate a value that really is along that red line. And so what I'm going to say is, all right, that's my equation for the line. I'm going to say my linearization of this function is that particular line. So then we're going to make kind of an assumption here that I'm going to say that if we're going to look at values of x close to a, I'm going to say my function is approximated by my linearization. That's the whole point. I want to get a simple equation to estimate what the values of my function are around a. Now obviously when you go very far away from a, then you become less precise. But very close to it, even in my sketch, you can see that the two lines are almost indistinguishable. So the word here is linearization of the function at a. So there's a different linearization for any value of a that you put along the function, right? If I designate a different point a, then I'm going to have a different linearization, right? Because the slope changes and the position of the line changes and all that. So this is really kind of the theory of it. There shouldn't be anything new here for you. It's just a matter of We rearranged a formula that we've used before, and we're going to call it something and use it for something very specific. Okay, you up with me on the notes? I know I've kind of scrolled out a lot of things real quick.
What does squiggly line equal sign?
That's approximately. At least in the context that I'm using it there is approximately. Okay, so let's go through an example. And so what I want to do is I want to find the linearization of this function, f at x equals square root of x plus 8 at x equals 1. Okay, when you think about this, you plug in a 1 and you get the square root of 9, which is 3. You know the function calculates very easily at that one particular point. But what I want to do is I want to use this to approximate the square root of 9.02 and 8.98. So here I have a known value for my function, and I want to calculate some values that are around the function. And so obviously in your calculator you can just plug in the square root of 9.02 and get your answer. But that's going to be besides the point, because we're going to assume that on a large scale we can't actually evaluate the function explicitly. So how are we going to do this? We're going to use that linearization. So the first thing we're going to do is take the derivative of our function. And you've seen that before. And then we're going to evaluate the function about the point that we're doing the linearization. So we're going to linearize it around x equals 1. And so we know that the function at 1 equals 3. And then the derivative of the function equals 1 over 2 times the square root of 1 plus 8. You evaluate that, and we get to 1/6. So we get a nice tidy slope there. And then I'm going to put it in my linearization formula. Now, you have two choices here. You can either memorize this formula, or if you remember how to make an equation out of a line, just remember how to take the 1 or 2 steps that it takes to rearrange your y equal, or y minus y1 equals, mx minus x, x1, to get there. But this is something that is a fairly standard way of representing the line here. And so when I plug in the values that I know, I have this, and then I'm going to simplify it. And so here I have this linear equation that around x equals 1, I'm going to get values of this function approximated by this linear formula.
Can you go back one slide really quick? Just
Yes. What was the question?
Oh, I'm sorry. Could you go back one slide really quick, just so I can look really quick how this version of, I guess, the point slope formula is?
So what we did was I went from here and just plugged in the values that I have, f at a, f prime at a, and a as my y1, m, and x1, and then just bring over that minus f at a to the first term there. Okay?
So L of x is the approximation, and x is the values you want to plug in?
Yes. Okay, so now let's get to the point of what we want to do. That we want to take the square root of 9.02. Now it's important not to put the 9.02 as x, because that's not what x is. X is 1.02 in this case, right? Because look at our function. The function is the square root of x plus 8. And so if we want to calculate the value of 9.02, we have to see what does that x plus 8 equal. That's 9.02, so x equals 1.02. So we'll stick that in the equation, and we calculate this out. And if we compare it to what we get out of our calculator, you can see that I'm all the way to the 6th digit before there's a difference. So for this particular function, this is fairly accurate. I mean, it's probably more accurate than you probably could ever want to use on most engineering and science applications. So if we look at the other point now, we know that the value that we're looking for x is going to be 0.98, right? Because we're adding that to 8 to get to our value. And so we have 2.99667. And so when I actually plug that into the calculator, I have the same number of good digits. You know, it takes me all the way to the 6th place to see the difference. Yes, Cassandra?
Where'd you get the 1.02?
The 1.02, if I look at my function here, okay, this is what I'm using this linearization. So when I want to calculate this, what I really want to do is have x equals 1.02. Okay, so you see, there's your function, there's your x value.
So is
Okay.
linearization something that we use instead of a point slope when we have a radical? It's just something that because we have a radical, we can't, we call that.
No, what you want to end up with is an equation that computationally is simple. Okay, multiplication, division, and addition. Any function that you have that you can take the derivative of, you can linearize.
So we actually want to forget the point slope formula.
Well, no, the
Instead
point
of-
slope formula is what allows you to do that.
Right.
Okay, because the point slope formula is the basis for saying I have a function value, I have the derivative of that value, and then I have the value a in there. So that's the kind of the key that gives you the linearization.
No, I guess I understand, but this is like, so we want to, this is an improvement based on the slope formula, and we want to use this instead of the slope formula.
It's really just a rearrangement of it. It's not really an improvement. Now, before I've had you calculate the equation of the line through that point, and if you did it with this particular one and ignore the fact that we're looking at, well, no, we're going to do it at a point 1, you're going to get y equals x over 6 plus 17.6. That's the way it was before.
So I guess, like, I mean, because you kind of said this is the hardest thing about these maths is now we have a new tool. When am I going to use this tool? When is this tool superior to point slope, just a simple point slope formula?
It's identical in what it's telling you.
Okay.
This is an application of it where we're starting to talk more formally about the language more than the actual math behind it. Okay, so on one hand, we were talking about the equation of the line tangent to a curve. Now what we're saying is, I want the linearization of that curve at this particular point. So the two are the same way, or are two different ways of saying the same thing. What is my linear equation that describes that tangent line?
It does in that way.
It is the same. This is not, nothing should be like brand new math here. This is more really a matter of language and terminology than it is, you know, anything new and any new revelation, right? I mean, we've dealt with tangent lines before, and we've dealt with the equations of tangent lines. We're still dealing with the equation of a tangent line, and you should see that the linearization is the equation of the tangent line. But when we do this linearization, in the context of how you would do science or engineering work, that would be a better way of describing what you're doing. Okay, so imagine that we want to do this over a number of different points. Like if we're using, we're trying to develop a weather map, and we're trying to develop a weather model, we would take different points on the map, and so we might have 1,000 points there, and so we would use 1,000 equations to describe what's happening there. We wouldn't use the differential equations that describe wind blowing. We would use a linearization of those things to make the computation fast. Yes, Carol.
Sorry, how did you get, for the 8.98 in the blue writing, how'd you get 0.98 for x?
I calculated this one right here.
Yeah.
It's the same thing. Go up to here, and you say, how do I make this 8.98? I make x equals 0.98.
Oh, okay.
Okay. So that brings up the point. There's more than one way to get a function that when we stick in an x value, you can get the square root of 9, right? And really, if you work out different functions, like if we said, if it was x plus 7, and then we would do the linearization around x equals 2, we would actually end up with exactly the same thing. Okay, so part of the newness of this is that you're going to somehow arrive at an equation that's going to come out of your physical model. We're not dealing with that here. We're a math class, so we're assuming that it's existing. I say that tongue-in-cheek more than anything else, but what we're really trying to do here is say, okay, this is the science behind it. It tells us that this function is what describes our system. The mathematics behind making something that we can compute very simply is to make use of the function and its derivative so we can calculate many points very quickly. If we were just trying to calculate this one point, what's the square root of 9.02? Wouldn't bother, right? In fact, if I just assign that to you, what's the square root of 9.02? You'd reach for your calculator. This is the process of setting up a linearized model. Okay, so I'd like you to try one. I'd like you to find the linearization of this function, 1 minus x, and I want to go around x equals 0, and I want to use that to estimate values of the square root of 0.9 and the square root of 0.99. Okay, so the first thing that we want to do is we want to calculate the derivative of this thing. Now, a lot of you calculated that derivative wrong. Notice the inner function on this thing is 1 minus x. And so by the chain rule, you take the derivative of the outer function, which is 1/2, and then the exponent is negative 1/2. But then you have to take the derivative of 1 minus x, which is going to be negative 1. And so we have negative 1 over 2 times the square root of 1 minus x. So then the next thing that we do is we're going to evaluate both the derivative and the function at 0. And so the function at 0 is 1. The function of the value of the derivative at 0 is going to be negative 1/2. And then we set up our linearization. So we put in f at 0, f prime at 0, and of course our x1 is 0. So when I actually plug in the values, I get 1 minus 1/2 x. And so when I plug this in, I'm going to know that x equals negative x equals 0.1, right? Because 1 minus 0.1 equals 0.9. And so when I put in 0.1 in my equation, I get 1 minus 0.1 divided by 2 is 0.95. All right, and then I can use the same function, and I get 0.995. And so when I look at what my calculator tells me directly, if I just calculate the square roots, see on that first one, I'm not quite so accurate, right? I'm about 2/200ths off. But on the next one, it looks like I have it good to 5 places. So just one more decimal closer to your kind of the center point, which is at 0, gives you a whole lot more accuracy. And that's exactly what you would expect. The closer you get to whatever the center point of your linearization is, the more accurate you're going to get. Now the other thing is, think about what this equation tells you also in terms of making estimates. Now, maybe you won't ever have to do a big computer simulation or something like that, but understanding behaviors like this allow you to make estimates in the field on something as well. So right now, if we look at, okay, what's the square root of 0.99, you know that you take the difference between 0.99 and 1, which is 0.01, divided by 2 and subtract it from 1. I mean, there's a real nice, easy way that you can calculate a square root. So if you find that there's an important square root for you to do, you do a linearization, and then it becomes kind of a mental exercise that you can do estimates like this.
So for the negative 1, I have to admit that confuses me a little bit because we're told over and over again that when you have an x inside an article like that, you have the opposite of x. It really is the opposite of x. I'm having, like, it's hard for me to wrap my brain around the idea that that actually is a negative 1.
Well, if we have a function g at x equals 1 minus x, what's g prime at x?
Negative 1.
Negative 1. And so if we're going to take f at g at x and take the derivative of this, this is going to be f prime at g at x, which is that first part, which everybody got, but then you take the derivative of the inner function, which in this case is -1. It's core to the chain rule.
So basically, like, it just does not matter. I just need to remember it does not matter that it's inside a radical.
When you're doing the chain rule, be very blind as to what you're doing. Do it very mechanically. Outer function is the square root. Inner function is 1 minus x. Okay, and then just do it blindly, and you'll end up where you need to be. Don't try and outguess your negative signs and things like that. Okay, so now we're going to do something. If you like the characterization of those lines as a linearization, we're going to do something very similar to that again, but we're going to do it by using the term differentials. And so what the motivation for this is, you'll see it's used in estimating possible errors, and it's also used for estimating small differences in overall functions. And just to jump to my example after the next one, let's say you have a hemisphere that has a 50-meter diameter. If you're going to put a coat of paint on it that's a 0.5 millimeter thick, how much paint are you going to use? And so, well, it's going to be the difference in the volume between a 50-millimeter hemisphere and a 50-meter hemisphere and a 50 plus 0.1, I'm not saying that right, plus, it's going to be the difference between those two hemispheres, the slightly larger one and the inner one. So we can talk about small differences and say, okay, if my x changes, how much is my y going to change? And so this is the same concept as our linearization. Linearization, we're interested in coming up with a value. With this kind of differentials that we're talking about, we're looking at what's the difference in the value that we're going to get. So the main idea of this thing is that we're going to take the derivative, of course, as the rate of change, and that for a chosen difference in the x. Now notice I'm calling this dx, and we've used the difference in x before as delta x, and I'll show you on a graph why they're different. We're going to choose a dx, and we're going to try and estimate a dy out of that. And so we're going to do a little kind of algebra here that says, all right, dy dx equals f prime at x. I'm going to restate that to say my differential of y equals f prime at x dx. And so what this is saying here is that if I know the rate of change of my function and how much I'm going to change my x value, I'll know how much my y value changes. So here we're not looking necessarily for the value of y with the value of x. We're looking for the value of the change in y given the value of the change in x. That good, huh? Okay, so let me kind of revisit a graph that I've had a number of times. So let's say we have this thing, this function now, that I'm going to have a as one of my basic points, and then a plus delta x is going to be that other point. And so f at a is going to be here, and then f at a plus x is going to be right here. So I'm going to call this difference, this rise, is my delta y. So delta y is just the difference between f at a plus delta x minus f at a. Notice this looks suspiciously like our derivative formula, you know, when we were doing limits of the derivative where delta x goes to 0. What I'm going to do now is I'm going to overlay my, my line, my tangent line, and that's in green this time. And I'm going to say, okay, I have the ratio between if I'm going to say I'm going to change my x by this amount, so my delta x and my dx here are going to be the same thing. But notice that my dy is different because dy is based off of that line. It's not based off of the curve. All right, so you would think, well, a differential, maybe that's more accurate than the delta y. It may be closer, it may not be, or it may be smaller, it may be larger, it doesn't really matter. In this way that I graphed it, of course, dy looks a whole lot bigger than delta x, or delta y. So the slope of that line, of course, is the derivative evaluated at a. And so with what I'm going to try and do is I'm going to try and estimate how much my function is changing based on my f prime times dx. So we're going to try and use dy to estimate delta y. And so since delta x and dx are the same thing, those two expressions, f at a plus delta x and f at a plus dx, those things are equal. That equals this point right here, or this value, I should say. But what I'm going to say is that it's going to be approximately equal to the function at that value plus my delta y. And so this thing here, I'm going to say, if I add my delta y, my dy, to f at a, I'm going to end up with an approximation of this. Okay, so when I rearrange things, I can make this approximation when my dy is very small compared to my, my function. This is not a good estimate according to my graph, right? I mean, I'm way off on this thing. It's like double what delta x is. But there again, if we go to very, very small delta x's or dx's, we should get a good approximation, and we can use the derivative to actually calculate the difference without having to use the function to calculate what the new function is, the new value, the old value, and take the difference. So let me give a more tangible example to see how this thing works, okay? So let's say I'm going to measure a circle, and it's going to be measured at 30 centimeters. The measurement error is going to be 0.2 of a centimeter. So what's the maximum possible error that I get in calculating the area of the circle? Okay, so I can calculate the area of the circle. That's easy. That's going to be pi r squared. But if I know my r could be off by 0.2 of a centimeter, how much off could my my area be? So this is kind of an error analysis thing. So of course my area is pi r squared, and if I look at my differential, and here I'm taking the derivative just using that d as an operator, and if I took dA over dr, I'd get 2 pi r. But notice I did it a little different. I took my differential operator on both sides, and then I took the derivative of that pi r squared, and I'm using the chain rule, so I have d pi r dr. And so my radius is 30. My dr is 0.2. And so if I put in my values, that means my possible error could be 37.7 square centimeters. Okay,
Wait,
so
is it derivative times the derivative?
it's not the derivative times the derivative. What you're used to doing so far is this. If a equals pi r squared. And so we take the derivative of this thing. R is the variable, right? So we're going to say 2 pi r. Well, I'm not going to really do that. What I'm going to say is I'm going to take the differential of a and the differential of my area. And so if I follow my rules right, I have this as pi times 2r dr, right? The chain rule. Because I'm not suggesting that I'm taking the derivative with respect to r. I'm just taking the differential of this function. And so now if I solve for this, if I divide both sides by dr, I do get the same thing. But it's important to retain the dr because we're really not taking the derivative. We're using derivative rules. We're calculating the differential. Okay, so I'm going to introduce some new terms to you here. These are three important terms. Okay, so my absolute error, what this means is what is my actual error? Okay, so the error is 37.7 square centimeters. It's exactly what you calculated. It has the units of measure of what you're calculating. Then we have something called the relative error, which is how much is the error compared to what I'm overall measuring. So is 37.7 a big error? I don't know. If we compare it to the area of 2,827 square centimeters, that's going to be 0.0133. And so I can put my relative error into the percentage error just by multiplying it by 100. And so I have a 1.33% error. Okay, so oftentimes you compare this with the measurement error. And so my measurement error is 0.67%, right? It's 0.2 divided by 30. So with a measurement error of 0.67%, I can get a calculation error of 1.33%. Now, the clever way to use this kind of analysis is to figure out ways of doing your calculation that actually decrease the error as you're measuring. You know, certainly you don't want to have a 1% error in your measure translate into a 5% error in your calculation. It's possible sometimes to have techniques where you're going to make some set of measurements and you might have a 1% error leading to a 0.5% calculation error. And so this is you talk to a machinist and they spend a lot of time figuring out how to machine things so their measurements actually don't compound, that they actually have ways of reducing the error as they go along. And a machinist will look at you kind of funny when you ask him about that, but when you start describing it, he'll tell you, he or she will tell you what they actually do along those lines. Okay, another example is what I had about the painting the dome. That's 50 meters. I want to put a coat of paint on it. That's going to be 0.05 centimeters, so that's a 0.5 millimeter thick. So I know the volume of a sphere is 4/3 pi r cubed, and so the volume of my hemisphere is going to be 2/3 pi r cubed. And I'm going to look at my differential volume. If I take the derivative of both sides, I look at my differential volume as this. So notice it's a function of both the radius and the thickness of that coat of paint that I'm going to put on it. And here's the trap. You need to make sure that your units are in the same set of measurements. So instead of centimeters, I'm putting that in meters. And so we have the difference in volume would be 1.96 cubic meters, which suggests I'm going to use 1,960 liters of paint to paint this thing. And so you see what I'm doing? I've calculated the volume of the dome, and I've calculated the volume of the dome slightly bigger with a coat of paint, and I'm taking that difference. But I'm not doing it by calculating the volumes explicitly. I'm doing it by taking the differential. How much difference does it make in the volume of the hemisphere if I made it 0.05 centimeters larger? And so here we're taking something that doesn't involve error analysis, but it's using the notion of if I make a difference in my radius, what's the difference in my volume? And that's really what it boils down to. So I know it's the end of class period. Take a look at the slides at the end and see if you can do this. It'll have the solution there, but work through this particular one before you try and do the homework. It's basically just finding the error in a cube. It's just like the problem that I did before the paint demonstration.